Everyone, so in this video we are going to discuss about separation of variables method. Now we can use this separation of variable method to solve differential equations if your differential equation is separable, which we learned in the previous video. So what is this method about? So the name of the methods gives away the approach to solve a differential equation, which is separation of variables. So what does that mean? So usually these first order differential equations have two variables, right? That is what you have seen up to now, y and x, for example. So the goal of this method is to first separate these variables in the two sides of the differential equation. That means, let's say I want all the terms with variable y on the left hand side. That means only terms with y on the left and all the terms with only x in the right. So you completely separate the terms with variables y and x on the left hand and right hand side respectively. So from there what you do is you integrate both sides. So let me show you an example. So dy over dx is, let's say, g is a function of x times a function of y, which is h. Now how do you do the separation? Here you have to have all the y variables on the left, right? So let's identify all the terms with variable y. So we have dy and we have hy. So dy is already in the left. So let's take h to the left by division. So we can take h to the left by division because we have to divide because it is product with, it's multiplied with g, right? Okay, so that is how you have y variables in the left. Now x variables, g is already in the right. So let's take that dx term to the right? Because dx is in the left hand side, in the wrong side. So how can you take that dx to the right? We can multiply by dx, right? Because dx is in the denominator. So here's what we can do. Now, so dy, we take h by division. So that's on the left and g on the right and dx by multiplication on the right. Okay. So then we have this result. Now what we do is we integrate both sides. Okay, so once you integrate, here of course we cannot integrate because we don't know what is h and g, right? Now once you integrate, you get two sides and you solve for, if the question is asking for explicit solution of y, you have to make y subject. You will see all that in an example. But here's the purpose of this video. Now what I have in this green color box, this integration result, that's a correct statement, but the process that I explained you is wrong, mathematically wrong. I did something wrong here. The mistake that I did is I treat dy over dx as a fraction. Well, you might ask, well, dy is the numerator, dx is the denominator, it's look like a fraction, isn't that a fraction? The answer is no. That's the notation for derivative. Okay, it's called Leibniz notation. It's not a fraction, it's the way you write the derivative. So then you might say, well, what you come up with here is wrong also, because if the method is wrong, then we cannot technically take that dx term to the right because it's not the denominator, right? It's a notation. How can you break up a notation? But here's the thing, the result is correct. As I said before, the process or the argument I made is wrong. So let me show you the correct argument because it's very important to know these things correctly. So let's start with the same equation. So differential equation g and h. Now again, the idea doesn't change. The idea of the method is to separate the variables. Okay, so we take that h to the left by division. We can do that, right? Because h is a function, it has nothing bad. So we can have as 1 over hy on the left, but the problem is we cannot take dx to the right. Okay, so that's the problem. So let's not do that because it's wrong. Now what I'm gonna do is I'm gonna integrate both sides with x. So 1 over hy. So I am gonna integrate both sides with respect to x, right? So that is why I need to have this dx on the left. Okay, here an extra dx, so here also there will be extra dx because of course I integrate with respect to x. All right, now here's the big argument. Now here this statement is very interesting statement. That is the definition for a differential. If you have learned it in calculus 1, you might remember what I say. If you don't remember, that's fine. So this is the definition of a differential. So dy over dx times dx. Now what do you think this is if you simplify it? Well, you might say that dx and dx cancel out, so this should be dy. Again, yes, it is dy, but you cannot cancel those dx because dy over dx is not a fraction. It's a notation where you write the derivative. So how can this become dy? Okay, here's the argument. Dy over dx is the rate of change of y. Now digest this very carefully. Dy over dx is the rate of change of y. Rate of change of y times the change of x is the change of y. Here's the better way to explain it. I know it's hard to digest. I know you will be staring at me right now in this video. Here's the correct way to another way to understand this. Let's say what is velocity? Velocity is change of distance divided by change of time. Right? So velocity is rate of change of distance. Okay? Now if I multiply velocity by change of time, what do I get? Change of distance, right? If you just take this term to the left. So that is exactly what happens. Velocity is rate of change of distance. Dy over dx is rate of change of y times the change of time. That means change of x is change of distance, which is dy. Okay, so that's another way to explain it. Okay, but this is a definition. This is the definition of differential. If you have forgotten it, you can Google it probably. So because of that definition, here we can write 1 over hy times dy. Instead of having dy over dx times dx, we can write dy, and we can write this statement. Now this statement is the same thing. It's the same thing that you get here if you treat dy over dx as a fraction. Okay, but it's wrong. But if you do that, anyway, you end up at the correct result. Okay, so it's just for one time in the life I wanted to show you the correct mathematics behind it. Okay, so most of the people would do it in the wrong way, like treating dy over dx as a fraction. Yes, you can do it. No one will see that. No one will see that. No one can read that from the paper, but you will still get the correct answer. But I wanted to explain you what's going on really. So let me show you an example. So dy over dx is equal to negative x over y. This differential equation. So let's solve it. What is the idea? Take all the y to the left, x to the right. So we can take this y to the left by multiplication because it's on the denominator. So y times dy here. Take dx to the right. So negative x times dx. Now I know I did the wrong thing treating dy over dx as a fraction. But we know we can do that. Even though we do the wrong thing, we end up at the correct result. Right? So that's what we proved. So let's integrate both sides. So if you integrate y, we get y square over 2 here. If you integrate negative x square over 2 plus an arbitrary constant. So this is the solution, implicit solution of the differential equation. Implicit means we cannot explicitly say this is my y. Okay, here y is not the subject. But if you want the explicit solution, what we can do is we can make y subjects by taking this 2 to the right. So y square multiply this side by 2, and then we can take the square root, right? So this is the explicit solution. Explicitly we found y because the unknown is y. This is the dependent variable. That is what you're solving for. This is the explicit solution. This is the implicit solution. You will see lots of examples in upcoming videos, but that's the correct mathematics behind separation of variables. What is the final summary? Dy dx is not a fraction. Okay, but you can treat it like a fraction, but at the end of the day you end up at the correct statement. Okay, all right, I will see you in the next video then. Thank you.